Okay, so maybe what we'll do now is we'll talk about the concept of digital photography. The reason I want to do this is that I want to show you, we're about to talk about some crazy matrix stuff, right? And the prerequisite of the class is that all of this exists in the background and you have some compelling reason to spend 8 years of your life studying how to solve these problems. But when's the last time you all turned a digital photo into the corresponding matrix that encodes it? Oh, never? We should probably spend 5 or 10 minutes talking about that, so at least you have some idea of that particular problem, which is a major source of input for people that solve what they call inverse imaging problems. There's some scattering problems here. This gets into MRIs. It gets into X-rays. There's a lot here, right? And also, you've heard all that's machine learning. The input to machine learning algorithms on digital cameras is the actual thing that we're going to talk about, which is the matrix model of the image that we're looking at. So this example that we're going to look at right now, this is called example 3.1.8. This is called a matrix model of a digital photo. And for now, could you guess which one we might start with if we wanted this to be as easy as possible? Before we had color TV, we had black and white TV. So if we're trying to get our head around how this particular thing works, could you guess where we might start? Black and white, because that's just one version. RGB is then 3 times that. You have a red photo, a blue photo, and a green photo that you superimpose on top of each other, and then the linear combination of each pixel correlates with the corresponding color that comes up in the end pixel. Quite literally, it's a linear combination. And then when you look at those things superimposed, you get a photograph of the real world, right? All right, so let's create a model for a digital image that uses matrices, that relies on matrices. I actually need to do this. Let's imagine a scenario. So here we have this person walking about life, thinking to themselves, I would like a more accurate body. And then they've got this thing, which is a very long arm, an extremely long arm actually, an out of proportion arm, holding a huge camera. And that camera is going to be pointed into space. And this person might have in mind a particular portion of space that they want to capture in that camera. So you might call this the continuous physical image. And then you might call this the digital camera. And the claim is this digital camera is going to turn whatever's in this site, whatever's in that thing, into a matrix that stores light values, basically. Right? So we're going to call the digital image a function. This took me about 3 weeks to figure out, by the way. Yeah, to figure out how deep I wanted to go, I had to read like technical journals in photography. You know how hard it is? There's some really cool chemistry behind this. To turn basically light gradations into electric signals, that's a non-trivial problem. There's a lot of chemists, there's PhD in chemistry that have spent the last like 50 years working on that. Do you know that chemistry? Neither do I. But I better learn it if I'm going to present this in class, right? Yeah. Okay, so we're going to say that let's create a function f which goes from our physical image D into R, where the domain D is going to be the set of all x comma y such that x sub L less than or equal to x less than or equal to x sub R, and y sub L less than or equal to, I suppose this should say y, so there's a typo in your notes there, less than or equal to r sub L, y sub R. this is a subset of what we call R2. And the thing that I want to say here is if we think about this D as the continuous image, we could actually impose a coordinate system on D, right? We could say to ourselves, okay, well, why don't we call the thing around the horizontal, we'll call that x sub L and x sub R, and those are just physical measurements that exist in space. Could you guess what we call this one? Yeah, really we should call it like y sub D and y sub U, down and up, right? But if you just turn your head to the left, you'll be fine, right? You gotta crank your neck and make it crack. Okay. All right, and then what we could say is that any point in this space, x sub y, that point represents the corresponding coordinate axis imposed into physical space, right? And then we could say that f at that point equals the amplitude of light at the spatial coordinate x comma y. And what we mean is amplitude meaning to say the real value to encode intensity or brightness of the image at x, y. And then maybe you say, I mean, now you have to make a choice, right? This is a really, really nice one. Do you think that black corresponds to the existence of all colors or the absence of all color? You might say that black represents the absence of all color. So if you were to look at this thing as x and y, I mean, you could physically measure this out, right? Maybe you say that this is like, I don't know where your 0, 0 point is. We might impose that the 0, 0 is always at the bottom left pixel. Or you might impose that the 0, 0 is always at the top left pixel, right? Okay, if that's the case, then maybe you say that this thing over here gets like, I don't know, in meters perhaps, right? So it is like 2 meters. So that would be like 2 comma 0. And then this would be something like 0 comma 1.5. And then this one down here would be, yeah. And then if it's an R2, we can actually get to any specificity. So we could go to like pi over 2 units, right? Because mathematically pi over 2 actually exists. Physically, do you think I could actually get to exactly pi over 2? Yeah, and I'm reminded of one of my favorite people ever saying, all you need is really 3 digits of accuracy after the decimal point, right? Like, depending on what your order of magnitude is, right? So if I got down to like post millimeters, I would start to have to get a pair of calipers. That's not necessary for this particular model, right? Okay, and then you could say like at this particular point, maybe you say that this is, I don't even know what this is, probably like 1.8 comma 0.25 or something like that. What's the f of 1.8.25? I would actually claim it's not 0. Because you see how it's kind of shining? This has to do with the actual property of this material, right? But if it was pure black, like a black hole, you might say it's 0, right? Like no light escapes from it, in which case I probably wouldn't be standing here, right? Yeah. And then this one you could say is the existence of all light, so infinity, right? Yeah, I mean now you have to impose, well, what is the highest caliber of light, but that gets into the sensitivity of your machine. Could you see the first problem with this model from the standpoint of capturing this in a matrix? And I want you to think, how much memory do your digital cameras have? If this is indeed an R2, how fine a discretization do I have? An infinite number of points. So just on the first top layer of this thing, I have an infinite number of points. What happens the moment I take that picture? My camera blows up, right? I can't store it. So you know the first thing that we do? Discretize. Yeah, discretize. We cut it up into smaller pieces. And this is why if you ever zoom in on a camera, do you ever recognize like, whoa, that's really pixelated? It's because you discretized, right? So the whole concept of a digital image is that we actually do something called sampling. So to convert a continuous image into a digital image, digital computation. This is engineering 11, right? I wanted to do a whole like 4 lectures on this because there's so much to this, but I just didn't have the time to do it last quarter. We sample, and in Riemann integration we would call this discretize. Is instead of having a continuous f of x, y, we do this thing where we sample it, and this is where I'm going to use computer, I don't even remember what you call this font. Courier, is it? Okay, do you see the continuous and the discrete? I know what you're going to say. God, that's beautiful notation. It's just the most gorgeous thing I've ever seen. You stop it. You stop it. All right. And so then, could you guess how we actually sample, what we do to that picture? Yeah, by cutting up D into M rows and N columns of pixels. Dun 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 dun. Dun 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 dun, right? So here was my original D. So here was my original D. And then we're going to sample D. And then what we would do with the sample is we'd actually just say, I mean, it really depends on where you want to go here, right? If you want to start right there, then you just say to yourself, okay, well, let's go every certain number of, let's do a uniform sampling. And then we would do a uniform sampling down here, right? And then could you guess what you do in between? Do you want me to fill all those in for you? Yeah, all the way down to here. At each one of this, there's a physical sensor in hardware that actually, when you're looking at the viewer of the camera, that correlates with a sensor in hardware that takes light information, turns that light information from a chemical signal into an electrical signal, and then the electrical signal is then sampled using probably an analog to digital converter to get the exact value of the light intensity at that pixel, and then the corresponding, maybe you say that each pixel has 8 bits. I don't know, maybe you say they have 16 bits. I mean, it depends on how much you want to pay for your camera, right? And then what you do is you just store, can you guess how many pixels that there's to be stored in? M by n pixels. Well, you could actually count, if you have m by n pixels and every pixel is stored in 8 bits, then how many total bits do you have? 8. M by n by 8. If it's stored in 16, then it's m by n and 16. And then the question was, well, how fine is your resolution? And that's where you start to see something quite expensive. You ever take a picture on an iPhone and then look at the corresponding picture, and then it says like 326 kilobytes? That's exactly what's happened. You've discretized your space, you've sampled your space. At every point in your space, you've sampled the light intensity. That is now stored as an 8-bit or 16-bit or you name it, depending on the architecture you're working with, number that represents light intensity, and then those numbers are combined into an entire picture that is stored as a data structure in memory, and then recreated on your screen by just sending the appropriate light intensity value to the corresponding pixel on your screen, and then when you see it, you see a digital image that represents the physical continuous space that you tried to capture in that picture. If it's black and white, it becomes much easier because each point, how many gradations of light does it have? Well, actually, 1, because black is just the negative of white. I mean, it's along the spectrum. I mean, that's a really bad way to say it. Black is 0, white is non-zero, right? Or vice versa. White is 0, black is non-zero, however you want to say it, right? I actually prefer to think about things in gradations of black, right? It's kind of a fun way to think about the world. All right, so now that you have that, you know what's crazy about this calculation, right? You can now reverse engineer this to create images that did not exist previously. So here's a 3-bit encoding for grayscale. So this is an example of how you might, if every pixel light intensity was done in 3 bits, 0, 0, 0 would be black, 1, 1, 1 would be white, and then you'd go accordingly, right? Do you see it? So every pixel now, when you're looking at the computer graphic F at a particular point, these are the total number of choices that you have, right? if f was 0, 0, 0, so if you look at a point and you store 0, 0, 0, what color would that pixel correspond to? Black. If you stored, let's try 0, 1, 1. 0, 1, 1 is 3 in binary, by the way. You get like the middle gray, right? 50% gray is what Microsoft Office would call this, right? And then if you stored 1, 1, 1, you'd get white. Okay, so now could you imagine if we wanted to create an image, how we would do that? And why don't I do the image that is closest to my heart? I know, I should really create my son's. Okay, so there we go. See if you can see it. You see it? What is it? What's it say? Love. It's the way I feel about this class.